Okay, let's start. So today here we have Jeroen Sijsling. I hope I am still pronouncing your name correctly.
Perfect.
From Ulm is going to talk about arithmetic Fuchsian groups and the canonical models. Okay, Jeroen, go ahead.
Thank you, Hassan. Thanks for the introduction and, of course, for the invitation here. So, yeah, I will be telling you about what the slides say here. And I should mention that the last time I wrote something about this was 3 years ago. This is something that I did for my thesis, and then 7 years afterwards, for reasons that I will tell you about, which I will tell you. And that means that I'm going to keep it a bit more general because I don't quite remember all the details. But you'll see. I'm going to tell you the idea behind these methods, and in the following way, because this is the goal of the talk. I also mentioned the sources. I'll come to that. The goal is to explain what is an arithmetic Fuchsian group, first of all. So I tell you what a Fuchsian group is in some more general context and the geometric and topological meaning of these groups. And then I tell you what it means to be arithmetic. Now, then I tell you that if you fix the so-called signature of a Fuchsian group, there is a finiteness theorem. And this is proved by Takeuchi, and I will mention that and briefly discuss the proof. And then we will discuss two special cases, namely those groups with signature 1 infinity, as it's called, and 1e. And yeah, Takeuchi says there's a finite number of arithmetic Fuchsian groups with this signature, and you want to be able to describe those and the corresponding curves. And I will tell you how you can do that. Now, the sources that I use here are lectures on Shimura curves by Clark for the Fuchsian part. There's an article by Mochizuki about correspondences and hyperbolic curves, which tells you, which gives you a very nice criterion or a very nice explanation of this arithmeticity. Takeuchi is the classical work where he proves this finiteness theorem. We will do some Bailey calculations, so for that I will need this article by Klug, Mustius, Chiaron, and Voigt. And yeah, it's in the end about my own articles on these canonical models, which I will tell you about later. For now, I just want to tell you a little bit about Fuchsian groups, and that means that I should tell you about Mobius transformations. Well, Mobius transformations are transformations of the upper half plane that you get when you look at the group PSL2R. So if you have an element Z of the complex upper half plane, meaning with strictly positive imaginary part, then you can do the following. If I have a matrix A, B, C, D in SL2R, I can do this. And the result of it doesn't depend on scaling the whole thing, so it induces a well-defined action of PSL2R. Okay, now the thing is, these elements of PSL2R, they come in a number of flavors. You have probably seen this, but I just want to recap it because it's kind of essential to what we do. The first one, the sort of vanilla flavor, that's hyperbolic. That is a transformation that you get when the trace, the absolute value of the trace is larger than 2. And now you may say, hey, but we're looking at PSL2R, so how can you say trace? Well, there's only a plus or minus ambiguity, so this absolute value thing is well defined. Okay, if you have that, then it's hyperbolic. And up to conjugacy, you get this matrix over here. And that's a dilation. It's in fact a dilation along the geodesics of the upper half plane that are vertical. And all the other hyperbolic transformations, there are also certain dilations along geodesics. That's one flavor. These elements, I call them vanilla because they have no fixed points in P1 of C. Well, wait, in H, in fact. So, right. Then there's another one. What happens when the absolute value of a trace is equal to 2? Well, it's called parabolic, and it might be plus or minus the identity, but if not, then up to conjugacy, it's this special element 1101. You can show that now gamma has a single fixed point in P1 of C, namely, in this case, infinity for this particular gamma. And that point, that fixed point, also in general, just belongs to P1 of R. Infinity also belongs to P1 of R. Okay, and the final flavor is elliptic. Those are these transformations for which this absolute value of the trace is strictly smaller than 2. And then up to conjugation, you have that gamma is of this form. And in fact, these particular gamma, they are the ones that fix the element I of the upper half plane. Okay. And yeah, in this case, also in general, gamma has two fixed points in P1 of C minus P1 of R. So in the union of the upper and lower half plane, and one of these is in H. And because this thing also has minus I as a fixed point, but we only care about the upper half plane. Okay, so those are the three flavors of transformations. Now, to get to the concept of a Fuchsian group, I need some other notion, which is discontinuousness. And you can phrase it a little bit more generally. Namely in the following way. You start with a group, call it G, and you have it act on a set X. In fact, it should be a set with a topology. I didn't write it down properly. Then there is a notion of discontinuousness. I don't know quite why it has this name, but discontinuousness means that the action is well behaved. It's slightly weaker than what is called freely discontinuous. Namely, you want the following: for every point X in this space big X, there should exist a neighborhood of that point U such with the following property, that if I look at all the G that map this U to another set U that still intersects the old set, that should be finite. You can also demand that it's just the identity, and then you get this free discontinuous bit, but that's not general enough for our purposes. And I will tell you exactly why this is the right thing, what this means topologically. But I want to tell you something first of all about how you can characterize these discontinuous groups. Okay, so suppose you have a subgroup gamma of PSL2R and X, the upper half plane, then you have an action as mentioned by these Mobius transformations. Now, the condition from a definition that I just wrote down here, you can show this is equivalent to what at first sight looks a bit stronger, namely that if you take a compact subset of the upper half plane in this case and the number and the element Z of the upper half plane, then this set, that is to say all transformations that map Z into this compact set, that should be finite. You can show the equivalence, and basically that goes as follows. This particular condition here, you can show that this is equivalent to, well, first of all, its stabilizers are finite because that's a special case. You just take a singleton. And also the orbits are discrete. That is more or less direct from this whole business with a compact subset giving rise to a finite number of elements. And if you have discrete orbits and finite stabilizers, then you can show more or less directly that you get a nice discontinuous map. And yeah, like this, because essentially use at every point in H as an open neighborhood with compact closure. Well, that's not important. This is a definition, and this is a criterion. For every compact subgroup, the number of, and for every point, the number of group elements that map the point into the compact subset should be finite. Good. And there is another notion that you can use for discontinuousness, and that is called a limit point. As before, you take a gamma, and gamma is a subgroup of PSL2R. And now I take an element Z, and I allow it to be in both in H, the group, the set that I usually am interested in, but also in its boundary, P1 of R. So the upper half plane with the stuff below and the point at infinity thrown in. Good. And you say then, you start with Z in this particular set, and it's called a limit point of this group if basically you can approximate it by a number of images of another point. There shouldn't exist a point W in H and some sequence of gamma n, also in fact gamma n distinct. I didn't write that, but that was stupid. I should have. These should be distinct, such that Z is the limit of this sequence of images. Yeah, so you should be able to reach Z by some sequence, some condensing sequence of images of elements of gamma. And why is it useful, and what does this have to do with this discontinuousness that I just told you about? Well, you are a limit point, in fact, in H, if and only if you're, for this group gamma, if and only if gamma is discontinuous at Z. That means to say that this particular condition here, oh, darn it. Only if it is not discontinuous. That was stupid. This should say not discontinuous. This is very tempting because it says discontinuous, and that's a negation anyway, but I meant not. All right. So limit points are those where you have a problem occurring, and basically we want groups that are discontinuous. So where this never happens, where all these Z, where there are no limit points in H itself. Right. And given gamma, you denote its set of limit points by lambda of gamma. And here is a main theorem, and I want to show you this because there are many ways to define a Fuchsian group, and this theorem gives you the equivalence of two of them, and I think it's instructive because it is something that you really have to prove. There is really content to this, and it's not just a definition thing. Because the theorem says, if I have a subgroup of PSL2R, again denoted by gamma, then this gamma is discontinuous if and only if it is discrete. And that is by no means something that you just get from first principles. You have to show it. Well, one direction is clear in this particular case, because your group, if you want to be discontinuous, you had better be discrete, right? Because if not, you just take a bunch of elements in the group that tend to some limit, has some bunch of distinct elements that tend to some limit, which you can do because it's not discrete. And then you take the images of some point under those elements, and you would get in the limit a point of, but it's not discontinuous. Okay, so that you need, and the nice thing is also that if you are discontinuous, then you are also discrete. Darn it! Or if you're discrete, you're also discontinuous. So for that, we do the following. Right, I told you that for to show that the group is discontinuous, you need that for if you take a point Z and a compact subset K, then this set that I wrote down here, not the G, the gamma in capital gamma with the property that gamma Z is in there, that has to be finite. Well, this particular set is nothing but gamma intersected with the set for the larger group PSL2R. And now comes the trick. I want to show that this discreteness suffices. So if I want to find a number of elements, and this is discrete, then it suffices that this set is compact. Okay, so we are reduced to showing compactness of this whole set for the group SL2R, which is nice and uniform. And for that, you do the following. Suppose we're sort of going to cheat because I'm right now a set that is not at all compact, as you know. But every compact set that you take is contained in one of these sets because it's closed and bounded. You can put it in here. And if I show the finiteness for this larger set that happens not to be compact, then I will also have shown it for all these smaller sets, K. So just take this K, and this K is a horizontal strip. It's a horizontal strip in the complex upper half plane, where this M and small and big M, of course, are positive, although I didn't write that out. Good. So I have to show that this set is compact. And for that, you have to show that if I start with some Z, I have to think of what comes in there. Now, the nice thing is, given an element Z, what exactly is the absolute value of a Mobius transformation of it. Namely, if I apply a matrix A, B, C, D, then I know that the absolute value of that is the imaginary part of Z over this square over here. That is something that you can calculate. I didn't do that, but it's true. And it means that, that's basically to end up in here, you get, first of all, from the lower bound, this inequality. And then from the upper bound, you get this inequality. And that is super pleasant because if you combine these two for C, D, A, and B in R, well, that defines you a compact set for these that bounds the coefficients A, B, C, D. That means that you're in a compact subset, closed and bounded of SL2R. That means that this set is compact, and then you're happy. So this is how this goes. I just want to say there's stuff going into this. You have to show it. Now, and I'm going to tell you right now that these groups, gamma that we consider here, these discontinuous groups, they are those groups that we will call Fuchsian. All right, are we okay so far? If not, please ask me a question. And can someone tell me that? Can someone say something? Yeah, okay, good. Because I just want to know that.
Yeah, no, I have to turn off my microphone. That's why.
Good. No, then it's all fine. I can hear my computer humming, so from now on I assume that it's all well.
Okay, well, good.
That is one fact. And like I said, this is a thing with content. We'll get to that later. Now, that means that if I'm interested in this topological action, discontinuity, discontinuousness, I can get loads of groups that have a discontinuous action just by getting some discrete groups out. You know, for example, groups generated by, well, often groups generated by a single element. And we also usually consider groups that are large enough in the set that their limit points are the whole P1R. Yeah, you can't have anything in H, otherwise it wouldn't be discontinuous, but you want the rest to be in there. P1R should be in there. And I'm going to visualize this for you. And for that, it is often useful to use a so-called fundamental domain. And the fundamental domain is just a part, closed domain, D, in this upper half plane with the property that if you take all the images on all the elements of gamma, then you cover everything. And moreover, if you take the open part of it, then it doesn't overlap. So it's basically up to some lies. It's representatives for every point up to the whole translation by gamma. Well, then I can show you what this looks like in some concrete example here. This is just a group, a Fuchsian group that occurs in nature. In fact, this is a fundamental domain for one of the groups, for one of the 1, E groups that you will see later in the talk. And I forget what E was. Well, I should add some angles together. I don't know. If I do it live, I'm going to say something wrong, but probably it's 2 or 3. Yeah, so this thing you see in the middle is the fundamental domain. Well, not just that one, also all the other ones, in fact, that are its translates. This is what you get by applying one of these transformations. And you see that indeed, if I now keep transforming under all of these transformations, then I creep closer and closer to the boundary, which in effect I didn't draw in the complex upper half plane, but in the hyperbolic unit disk, because it's prettier, but it's conformally equivalent. So this circle you see here is in fact P1R. We're just looking at it in a different way. And you see that every point on this P1R, you can just crawl very close to it by following these fundamental domains, meaning that you really get the appropriate limit set. Now, there's lots of stuff that I won't tell you about. For example, that these fundamental domains, they have very pleasant topological properties. You see these sides have some pairing that tells you how to identify them appropriately and to glue them so that you really get out what you want. If you do it in this particular case, in fact, you will get, if you get this classical donut or bicycle tire, whatever you want to call it, you get that out. There's theory on that which I will ignore for this talk, but I do want to mention one thing, namely that a Fuchsian group gamma is said to be a finite co-volume, as it's called, usually just denoted by vol in what follows. If the volume of this fundamental domain here, with respect to the hyperbolic area on the upper half plane, which is dx dy over y squared for x, the real part, and y, the imaginary part, if that is finite. And now I should tell you why we did this. We looked at some discrete, discontinuous groups. What does this mean in geometry, for example? And here it comes. Now, let's look at the Fuchsian group. Oh, did I define what a Fuchsian group was? I didn't. I'm really sorry. That somehow fell out. But then I'll tell you now in words. What is a Fuchsian group? A Fuchsian group is a subgroup of PSL2R that satisfies one of these equivalent conditions. It's discontinuous, or equivalently, it's discrete. Good. The fact is that now you can form this quotient. Of course, you can form it as a set that you know anyway, but this quotient also is a canonical structure of Riemann surface. And this is for the following reason. This quotient has a, or this orbit space, if you look at it, there are two flavors of points in this orbit space. And one flavor of point is those for which the, over which this action is free discontinuous, by which I mean that if you look at one of the points over a given fiber, you never get any stabilizers except the identity. Over that part of this particular orbit space, this map from, or the restriction rather, of this map from H to this quotient, there it is free discontinuous. And that's just really pleasant. That is this classical covering thing where you get all these sheets and they're just disjoint. And then you say, okay, what do I then give for the Riemann surface structure? I just say a function is holomorphic on an open subset contained in this nice part of the quotient if and only if this composition is holomorphic. There's one thing, and now there's the other thing, namely that you can also have that perhaps this set here that I defined, perhaps you're now at the point where you cannot quite make this to be a single element, but where it is finite. Yeah, finite is still good, because if you happen still to be finite, then you can show that actually that this group that you get that maps a given point P to itself is cyclic. And what you then get is a so-called elliptic point. The elliptic points are exactly those that are fixed by some elliptic element that I defined before. Remember, you had these elements. You may have some elements in your group that have fixed points, also in H. And if you get those, you have to take a bit of care how you define the Riemann surface structure there. But like I said, in that case, the group is actually cyclic of order n, say, and then you choose an isomorphism from the disk to the upper half plane, setting 0 to P, and then you say that the function is holomorphic if and only at this point P, if and only if this composition has an appropriate valuation, namely a valuation divisible by n, because in that case you can show that it is nicely invariant on the appropriate transformations, that you get a decent notion of holomorphicity. So that's how that goes. You just have to be a bit more careful around the elliptic points. But this is also very well explained in this reference by Clark that I mentioned on Fuchsian groups. Okay, so this is the fine print that makes it work. The discontinuousness assures that I can do this, and I get a structure of Riemann surface. This is still a bit too rich for my taste, because you get really a lot of Riemann surface, and I wanted it to be a bit tamer. And there's where the second condition comes in, the finite co-volume condition. Remember the condition that this fundamental domain that you get and that you can show under reasonable circumstances always exists has finite volume. In that case, you can show, well, it still has the canonical structure of Riemann surface. Of course, that's the last slide. But it's a bit better. It's not just any Riemann surface. Namely, first of all, you can compactify this thing and you still get the Riemann surface. Second, this quotient y gamma that you have, this has a finite number of elliptic points with stabilizers. That's what I mean by the order, that the stabilizers of these elliptic points have order m1 up to md. Yeah? I just have finite numbers, say d of such elliptic points, and these are their stabilizers, the cardinality of their stabilizers. Finally, this compactification wasn't a very big one. Namely, I only had to throw in fairly many points, say n of them. Yeah, there is no big open part missing it, but just some point that you missed to make it compact. There are n of those points, and in fact, you can show that these correspond to the conjugacy classes of parabolic elements in gamma. And you can encode this. So this is geometric or topological data that goes into your that comes from this Fuchsian group, and you put it in a signature. You put it in a signature, and the first bit says what is your genus of the compactification. Second says what are the orders of the elliptic points, and the final one says how many of these parabolic points do I get. Yeah, so the point that I don't quite see in the quotient, but that in fact are images of limit points on the P1R. That you write down in this signature over here. Now, the very pleasant thing is that the volume or the co-volume of your group can be expressed in terms of this signature. This is absolutely important. This helps you to prove lots of theorems. And it goes in the following way. The co-volume is 2 pi times essentially some Euler kind of thing, maybe 2g minus 2 plus n, but plus a number of parabolic points plus some combination of these quantities coming from the elliptic points. So that's great. I know everything about the relation between the volume and these topological data. Wonderful. Okay, next one. Yeah, we can invert this. So I told you if you get this finite covolume group gamma, you can make a quotient, and it has these very pleasant properties. Just misses a few points, you know exactly what happens over the elliptic points and where it ramifies and whatnot. Now the point is, this you can invert. So what we're going to do for that is just pretend we didn't do anything and start inverting the whole business. Right, so you start with a Riemann surface X of genus G, and it has a number of distinguished points, which are called P1 up to PD and Q1 up to Qn. No coincidence that here is a D and here is an N, because they also start with integers M1 up to MD, big or equal to 2. And then I say the following. I'm going to look at certain special maps to X. It's a map, a holomorphic map, in fact. I should have said that. Holomorphic map F from some other Riemann surface Y to your original surface X with the following properties. That this map should be unramified when I'm not over these points that I picked out at the beginning. That's one. And I'm also going to impose a little bit about the ramification indices at these points. So at these points, they may ramify. And at Q1 and up to Qn, I don't impose anything. That it can ramify in whatever way it likes. But I want that if I have one of these points, Pi, for one of I is equal to 1 up to D, then all these ramification indices should divide Mi. And you can study these things and show that it gives you rise to a good structure, namely of the following optimal kind. There's a universal such subordinate cover. If I just start with these points and the integers, I can make a largest cover with the properties that I just described. And all of the other covers, they are just subquotients of it. Yeah, this is something that is familiar from covering theory, if you have seen that, but it's just a little tweak. Okay, so you get a subordinate cover, and that is related to what we did. Namely, okay, so I repeated what I just wrote over here. Now, if also for the data that you started with, this quantity that also figured in this volume calculation, if that happens to be positive, so that you get a meaningful volume out in the previous slides, then all of what I just told you comes from a Fuchsian group in the following sense. For the open subset V, and there should be an X here, I'm sorry. For the open subset V, where I remove all but these endpoints from X, I have that this restriction is nothing but something that I know, the S quotient of H by some group gamma. Moreover, X, the one that I started with, the group that I started with is the compactification of this particular quotient, and the group that I start with just has exactly this appropriate signature. So in a nutshell, I can also just start with, I know that if I start with a group gamma, I get a quotient of this particular special kind with certain ramification indices, but I can also just invert it. I take a Riemann surface X, mark some points, put some ramification conditions. I say, now please give me this universal cover that corresponds, and lo and behold, that actually comes from a Fuchsian group. That is essentially you prove this using the Riemann uniformization theorem. So Fuchsian groups are of finite co-volume. I should have said that maybe, because it is a finite co-volume. Fuchsian groups of finite co-volume are just another way of looking at this particular data, this just completely geometric data. Good, and it also means, for example, that you know what these groups look like. Since you know that basically these Fuchsian groups are some kind of fundamental group, you know how to write down generators and relations form. You can do it in the classical way. You just take elements alpha I and beta I corresponding to the fundamental group of the compactification. Also gamma I and delta I corresponding to these points. And then you have this fundamental relation, which you know from topology. Moreover, because of this subordinate condition, you also get these conditions. So Fuchsian groups of finite volume are easy. You can just write them down like this because of the geometry. Good, that is something that I wanted to communicate. Why are Fuchsian groups geometrically and topologically interesting? Why is all that you're doing nothing but just another way of looking at Riemann surfaces and their covers? Okay, now we come to this arithmetic part. Or maybe I should, are there any questions so far?
Jeroen, maybe just one question before I forget it.
Yeah.
This inverting from a Riemann surface to Fuchsian group, is it, I know theoretically, but is it algorithmic? This means that if I give you a algebraic curve, do you have any algorithm or which gives me the matrices subgroup of SL2R?
No, not to my knowledge. This is a very transcendental thing. You go from an algebraic to an analytic thing, and that is always very painful. And also the converse, to go from the group to the curve, is also difficult.
No, from the group to the curve, at the end you want to construct this kind of this Eisenstein series modular form, and that at the end embedded in some projective space one gets some maybe algebraic curve. The other direction, I was thinking. Okay, anyway, go ahead.
Yeah, it's true what you say. Well, I don't know. I'll think about that. Yeah, now we come to these special groups, arithmetic groups, or in our case, arithmetic Fuchsian groups, and those use very special kind of Fuchsian groups. And I'll tell you in exactly what way. So my how do you call it? My supervisor Fitzbergus always used to say me an arithmetic Fuchsian group it's very easy. It's just something that fixes some lattice. That's how we like to think of it. And to make it a bit more precise, I'm going to describe you a framework to Margulis, which is very general, but which maybe makes more sense in just giving you the concrete definition. A Fuchsian group gamma is called arithmetic if the following happens. It should be a connected, non-commutative algebraic group. I don't know why there's algebraic twice here, but just ignore that. That should be defined over Q. It's almost Q simple. That means that basically you're simple up to taking some automorphism group. And you also want that if I now extend scalars to R, I can find a map, an algebraic map from this group that I just described to PSL to R, with the property that this map is essentially injective in some group theoretical. I had a kernel is super small, it's just compact, so negligible. And moreover, if I now take the image of the integral points of G, then it is commensurable with gamma. Okay, there's two notions here that are difficult. First of all, what is GZ? What the integral points of a group. For that you say, I take my algebraic group and I embed it into some group GLNQ. You can always do that with an algebraic group of this kind. And if you do that, then you can pull back GLNZ. Yeah, and you get GZ. You get the number. You get the inverse image of GLNZ in this group G for the particular embedding that you chose, and that is just what you call GZ. And of course, that will depend on your particular embedding, but this property of being commensurable that I described here, that will not. So GZ is a bit of a vague thing that is not quite well defined, but we don't care because we only care about groups up to commensurability. What is commensurability? That means that if two groups are called commensurable if and only if you intersect them, the intersection is finite index in both. So they're essentially the same. And these groups only change up to a commensurable amount. And this is where Fritz's remark comes from. Fixes some lattice means that for some representation on this GLN, it's just the integral points. That's how he thinks of this, except that this is now how you write it down in a very fancy way. Yeah, so why are these things relevant? There's a big theory by Margulis around this, which I do not understand, except for the part I need. But also because he generalized it amazingly, not just to Fuchsian groups and whatnot. But Margulis showed that these Fuchsian groups are exactly the ones for which the index in its commensurator is finite, yeah. So, or is it infinite? I'm getting super confused. I think it should be infinite. Yeah, this should be infinite. So, the commensurator are exactly those elements of PSL2R with the property that if you conjugate your group by it, it's again commensurable with gamma. And normally that doesn't happen very often, but for these arithmetic groups it does. And that makes it they're very special. And what you should think of when you see that this commensurator is infinite, you should think of Hecke actions. You should think of these arithmetic transformations you get from Hecke algebras, because those give rise to this amazing bunch of correspondences you can make. And basically this gives you a way to define Hecke algebras without talking about Hecke algebras by this condition over here. Good, so that's the reason to look at this. They have a very rich set of correspondences. Now, Mochizuki showed the following in this paper that I mentioned. And Mochizuki says this is something well known, and I'm sure it is, but he wrote it down, and this is something that is great when someone does it, because well known is, I don't like this word. And he just showed, and it's in his article, that a Fuchsian group gamma is arithmetic if and only if the following thing happens, which is much more concrete than what I just wrote down. Namely, the following should be the case. There should be a totally real number field F, whatever degree. There should be a quaternion algebra B over F. So this is an algebra defined by the classical thing I squared is equal to some element of F, J squared is equal to an element of F, and Ij and Ji anti-commute. And you want this quaternion algebra to have the property that if you tensor this, if you extend scalars by some infinite place, then you get the matrix algebra for precisely one infinite place of F. And you want it for all the other infinite places of F, you get the Hamilton quaternions out. You know, the ones with I squared equals to -1 and J squared as well. So just one should be M2R. And moreover, this should also exist in maximal order with the property that this gamma that I just found is essentially, that is up to commensurability, nothing but the image of this order. It's the elements in this order that under this particular embedding have determinant 1. That's just some special set, some special subgroup of SL2R, and those are the ones that interest me, up to commensurability. Images of these maximal orders, or rather of the norm 1 elements in there. Now this works, this is concrete. I just want to tell you, this is completely unmotivated if you give it like this, but this is something you can show. This is really the same as this more logical definition that I just told you about. Okay, now that's the definitions, and also a bit of a more concrete result by Mochizuki. And now I want to tell you about what Takeuchi proved. And Takeuchi looked in even more detail at arithmetic groups. And he, for example, shows you how do I, given an arithmetic group, recover this quaternion algebra and this total real number field. It's not clear. Also not from this description. You cannot right away see this. Takeuchi says, I'll just do this. You take the subgroup generated by all the squares in your original group. You call this gamma 2. Then F is nothing but the field you get by joining all traces of all elements in there. B is an algebra over F that you get by just writing down these matrices and adjoining them. That turns out to be an algebra. That is an quaternion algebra, and you get an order in B, which is just the same what I just said, except that now you do it over ZF and not over F. So that makes it possible to write it down. If someone now comes to you with this group gamma, you can find F, you can find B, and you can find O, the order. Good. In fact, Takeuchi did something more. He showed this finiteness result. I fixed a signature as before. Genus G, bunch of elliptic points, bunch of parabolic points. Takeuchi says up to PSL2R conjugation, there are only finitely many Fuchsian groups of signature S if you impose that they're arithmetic. There is no chance in heck if you do it for general groups of signature S, because you have, this is just topology. You can vary all the holomorphic parameters. There's no way. But if you want them to be arithmetic, then you get a finite bunch of groups. And it goes basically like this. If you start with your F and B, well, I'm just curious about what happens if I fix my field in quaternion algebra, then you can in fact show that if you have a maximal order, you know what its volume is. There's an arithmetic expression for it, which is a bit miraculous, but it's true. It was found by Shimizu, and it's this. Okay, I won't get into that formula until a bit later, but the important thing is that volumes behave very well under inclusions in the sense that they multiply by indices. So I also know that the volume that I write down here in terms of the volume of my arithmetic group can be expressed like this. I just put the relevant indices in front of the index of gamma in gamma 2 and the index of gamma 2 in P01, which is well defined because that's gamma 2 defined in order, so it fits inside the maximal order. Okay, now if you stare at this formula for long enough, then you see, okay, that means that I have some bound on that there is finally many possibilities from F, essentially because I can bound this part, and then there is a result by Odlisko that tells you there are really finally many total real fields that you can have here. Once you know once you fix your total real field, then you cannot have too many primes that ramify in your quaternion algebra. Ramifying primes, by the way, that is to say, primes defining the discriminant are those where you don't get a matrix algebra. It's always a finite number, but the important thing is that also here you have a bound on which primes you can have at all, because this norm cannot be too big. Your volume would be inappropriate. So you have a bound on the number of primes that can ramify, and then the theory of quaternion algebra shows there's finally many possibilities for B as well. And also for O, because of some generalities on type numbers, only finally many conjugacy classes are possible for these maximal orders. And since then, this gamma 2 is a subgroup of known index of this group, then by general principles, you're done. There's only finally many possibilities for this particular group over here. So yeah, basically, miraculous formula by Shimizu combined with strong bounds by Odlisko. And now, this is still theoretic, huh? It's not super easy to do this if someone comes to you with a general signature, but Takeuchi did that as well. Takeuchi looked at this at least in the particular cases of groups of signature 1e, that is to say, genus 1, 1 elliptic point, and 1 infinity, genus 1, 1 parabolic point. And he determined those classes explicitly, and that's really a great job. It's a long article. You need to do a lot of work, much more subtle with all these estimates to get this out, but he did it. He determined the PSL2 are conjugacy classes of these groups. And it turns out that you can describe them by a triple X, Y, Z, namely the trace of alpha, beta, and alpha, beta, where alpha and beta have the property that their, their commutator is, gives rise to this particular elliptic or parabolic element with a certain normalized trace. You can also show that you can express F and B in terms of these traces. So Takeuchi just says, voila, there they are. I just found this for you. And he did this by a very clever minimization argument that I won't describe, but really clever is the word for it. It's really great. I don't need to tell you about that though, but I need to tell you is how many there are and what you can still say about them. It turns out that there are 4 arithmetic Fuchsian groups up to conjugacy in PSL2R that have signature 1 infinity and 71 that have signature 1, e for some value of e. The largest one, in fact, turns out to be 11. Now, the thing is that you can also find the corresponding quotients. So given such a group gamma, you can take the quotient of the upper half plane by gamma. That gives you a Riemann surface with a special point, either parabolic or elliptic. And the question is, can you find equations for those surfaces? And the answer is yes. You can do it, and you can even do better. You can find canonical models for these surfaces. And that's what I will tell you about for all these gammas above. So for the 4 infinite cases and for the 71 elliptic cases. Yeah, it's difficult to write down this theorem, but the content is just that you can make everything effective and implementable. Okay, now I won't tell you all details, but I will just mention the 1 infinity case and then a special case among those, just so you see these things once. Here are 4 trace triples. You see there are 4 cases, Roman 1 up to 4, and these are the 4 triples that I mentioned to you before. And this is just how Takeuchi gives them. He says, okay, here's your group. Because if you do this, if you now have these quantities, then you can find alpha, generators alpha and beta just by saying, okay, alpha is some hyperbolic element, beta as well. And now if I equate all these traces appropriately, then I can find alpha and beta. It's just a finite calculation, a bit of trickery. Well, just quadratic equations. You can do that. Now in this particular case, this field that I mentioned before, total real field, is just Q, very familiar. B is M2 of Q, as simple a quaternion algebra as you can get. Even better, This group gamma squared, as I mentioned before, the group generated by the squares and gamma is of signature, well, not 1 infinity, but now with 4 points, 4 parabolic points, and even better, it generates an order like this, and you may assume it's to be included in M2 of Z, essentially because this maximum order is unique in M2 of Q. In general, you may have the complication that the units in O are larger than gamma 2, but we won't have that because we're going to look at a special case among these 4, namely case 2, where this was the trace triple, as I always call it. Now, it's very pleasant. You have 2 great things. First of all, if I look at gamma 2, this group is nothing but the units, the elements of norm 1 in this particular order. That is great because it gives me a very easy way to test whether an element is in gamma 2. I just check if it's in the order and if it has norm 1. Much easier than doing some horrible problem with words in a group. Moreover, you also have that gamma 2 is nothing but the intersection of gamma with SL2Z. And from that, you get this diagram that I wrote on here. You have a map from gamma 2 to gamma. That is, in fact, a Galois map with group Z mod 2Z times Z mod 2Z. It's nothing but multiplication by 2 on an elliptic curve. And you have a map from gamma 2 to the larger group SL2Z, which comes from a maximal order, namely M2Z. And you can show this is degree 24. And it's now easier. Yeah, this is what I mentioned already. You can manipulate with this group better because you have this description over here. So this diagram is something you can touch. Okay, well, I make it geometric. I take the corresponding curves. I'm interested in this curve on the left. So how am I going to find that? Well, I figured you just make this, you just make sure that you understand this curve first, and then afterwards just a multiplication by 2 elliptic curves, so it will in fact just be the same curve over C. And now the great thing is that this map of degree 24 is not just any map, because this map comes from an inclusion of gamma 2 into SL2Z, and SL2Z has signature 0, is unit 0, and 2, 3, infinity. That comes from the parabolic point and I and zeta 3. And that means that this map that I wrote down here, that is in fact ramified above 3 points only. And that's a Bailey map. And those Bailey maps are great. Bailey maps you can compute with. And Bailey maps then allow you, I will tell you how, to get this arrow out really explicitly. Because after all, this what is written here, you understand. This is nothing but the modular curve. Classical one. It's just a P1 minus 3 points. Yeah, the J, or if you want, on the level of a J line, this is the J line with the special values. J is infinity, 70, 28, and 0. And I just need to figure out what the map to that is, and I know what the other curve is. Well, this curve is genus 1, so it's not a completely trivial map. But you can get access to it because you have your group gamma 2, and because of it's a very accessible group, you can also determine the corresponding monodromy representation. You have this subgroup gamma 2 of the larger group SL2Z. And yeah, you just go ahead and write down cosets for it, 24 cosets, and you analyze exactly how the generators of SL2Z act on those cosets, and there you have your monodromy representation. And I won't write that down, it's just some bunch of permutations. But I will tell you what the map is. So the map that I want to find over here. That's a Bailey map, as I mentioned, and here it is. It's a very pretty Bailey map also. It's this map. You take this curve. That's well, it's a genus 1 curve, and you send a point a pair x, y to this. That's all. You see, in particular, there are some the elements over 0. They all ramify with order 3. That's no coincidence because it has to do with the point of order 3 in PSL2Z, and there is some the numerator is less uniform. It will give rise to the special 4 points on the elliptic curve. Okay, now how do I do this? I want to tell you in a nutshell how you write this down. Well, first of all, there's a general method to find such Bailey maps. This is why I mentioned this article by Klug, Musty, Schiavone, and Voigt at the beginning. You can, if someone comes to you with a monodromy representation, which you have, you can find the Bailey map. But in fact, while their algorithms work, they're not always extremely elegant in what their output is. So in fact, in this case, it's just better to pull all tricks that you have out of your head, and it turns out also to work. Now, this, you have a monodromy group. I mentioned there is a monodromy representation of 24 cosets. You know what that group is. You know, generators for the fundamental loops that give rise to the fundamental group representation. Now, you have the monodromy group and a stabilizer of 1 inside there, so that the cover is obtained by analyzing the quotients of G by H. And the pleasant thing is that I don't have to look at this just by itself. There is a nice chain of subgroups, H containing K1 and containing K2 and containing G, with these indices, which multiply to 24. And these are very pleasant because it means that also here you just get some other cover out, and covers of degree 2, 3, and 4. Well, that's something that you can write home about. So you just do that. You just first go up here. First, you look at this degree 4 cover, and by analyzing the action of the coset, you see this is it, if I label my points correctly. Then you look at this one, and again you see it stays, this K1 still gives you a genus 0 thing. It becomes this particular map, although that can't be true. There must be a, this X should probably go, okay, forget that X, I copied that incorrectly. Then there is this inclusion, that's just a 2-to-1 cover of a P1 that ramifies about 4 points. 4 special points that you get from the fibers of the cover that you found so far. And if you put all of that together, if you piece all of them together in the appropriate way, which is really difficult to do on a slide, so which I didn't do, then you get this map that I wrote down for you. But just pull the map apart is the main idea. Good. Are we there yet? Not quite. We are there in the sense that we now know what X gamma looks like, because I already told you this map here. If you choose an origin on this X gamma 2, which I just wrote down for you, this is X gamma 2, this is your curve on top, it just becomes multiplication by 2, meaning that X gamma is just the same curve. Here's your equation. But that's not good enough, because you also want a canonical model. You don't just want some model over C, you want a model over Q, and in fact you want one with the most pleasant arithmetic properties that you can get. I will tell you what it means. But in this particular case, it's a bit more concrete. I want a special model over Q, and I don't quite know which one to take yet, so what I have to do in practice is to take the Jacobian of this and then twist it by a relevant scalar. Just take a good quadratic twist. And the canonicity condition in this particular case boils down to X and Y having rational expansions of Puiseux series. And because remember, you have this map down to X SL2Z, and there you have this, they have the J function, or alternatively the Q coordinate, and I want that if I express X and Y in this Q, I get a nice rational series. And you can do that, they're on bottom here, and you have to take a twist by quadratic twist by -1, you get this curve, which is this curve in the LMFDB. There's a link, but I won't click it. Yeah, this is how you do it. You get a model over C, and the fact that these X and Y have to satisfy pleasant coefficients, if you express them in Q, that's fixes the only thing that you can still twiddle with, which is the quadratic twist. So this is the arithmetic part of the whole story. Okay, now I did one of these cases for you, and the other 3 cases are similar, just more technical. Let's keep it at that. There is a modular interpretation, all known cases, namely these curves, X gamma, throughout they parameterize elliptic curves with a distinguished torsion structure. Just it's not a simple one. It's not one of the classical gamma 0 of n things. It's a bit more exotic, but you can do it. They still come from congruence subgroups with a little tweak.
Jeroen, in the previous slide, there was this 2 elliptic curve, one degree 4, one degree 3. I was confused. Which one is the model for X gamma?
Well, over C, this one works also. But yeah, the thing is that if you want over Q, then so over C, what I wrote down here, and this one, they're isomorphic.
Okay.
But which one is the right one over Q?
The point, the marked point is in the second one is, I imagine that it's the point at infinity. No.
Yeah, exactly.
And in the first one, there are 2 points at infinity. So
yeah, and you would have to take one of these points. But yes.
okay, so there is a kind of involution in this moduli space then.
I don't know. No, it has just to do with the fact that I just wrote down an equation over C, and that I should instead have taken its Jacobian and.
Okay.
Well, because I also didn't tell you quite what was a distinguished point here. You can, in fact, this is x gamma squared, and these zeros. They are the 4 distinguished elliptic points on x gamma squared, of which there were 4. But then you take in the multiplication by 2, and if you do it arithmetically instead of just over C, then they all get merged into the single elliptic point on the on this curve over here. Over Q, it's a bit more subtle than over C. But in the end, they all these 4 merge into a nice rational point over Q, which is the point of infinity of this particular curve. And I don't know. I don't think this factors. Probably it doesn't. I'm not sure. Well, in fact, that we can find out. I'm going to click I'm clicking the link anyway, because the rest of the talk is a sketch. The LMFDB is useful for these things. It says, oh wait, it does have full torsion. Okay, so also this particular one has full 2 torsion. But well, yeah, you can take the point of infinity to be a distinguished point. Okay?
Okay, go.
Good. Then, yeah, there's another interpretation. You can use this interpretation, in fact, to find the uniformizing differential equation for these curves, which is a differential equation, the solution of which have an exactly the right monodromy representation, which the solution of which would give rise to the group gamma. You can get it from the periods, which is, I guess, also a theme in this seminar, but you can also do it much more directly. There is a uniformizing differential equation on the modular curve, and you just pull it back. You just pull it back along this Bailey map to your x gamma, or rather to your x gamma squared, and you push it forward, and that means that you can get your A out. Normally, this is a very difficult thing, but if you're in the presence of a Bailey map, it just falls out, comes out in the wash. Yeah, you get the accessory parameter, and this is a nice circumstance in which you can do this. Now, I'm gonna close this talk just by saying very rapidly what happens in the remaining case, because I didn't tell you yet what happens if you have a 1, E group. Now, lots of stuff is similar. You still get this configuration that I told you about before. There's this basically multiplication by 2 here, and the maximal order of a quaternion algebra, but now, yeah, of a general quaternion algebra, not of M2Q, and it's, as you don't know the total real field, it can be a bit big sometimes. And moreover, another problem is this group may not have a signature that is so nice. It may not be a triangle group. This may not be a Bailey map then. And gamma may not be commensurable with any triangle group. I may not have any way of getting at this with Bailey methods, and then also not of getting this accessory parameter. You get lucky in 27 out of 71 cases. And in that case, I also just, well, that was my thesis work. So in fact, we're going back in time, but this is my thesis work. You can find these Bailey maps over C, and then you still get this uniformizing differential equation where now n is equal to 1/2 over 1/2 minus 1 over 2e. But in the other cases, you don't know. You can't do it with Bailey maps. And this is how I do it. You use this canonical model theory. Because also, in this case, if you have a Bailey map, there is a subtlety hidden. What is the canonical model of x gamma? What does this mean at all? Yeah, over which number field is it defined? And how do I find it? And here I have to be very summary, but there's theory by Shimura, which was rephrased by Deligne, and I think Shimura didn't like this, but it's pretty neat how Deligne does it. And you can describe x of this maximal order as a connected component of a quotient like this. U is the unit of the upper and lower half plane, K is the compact open subgroup, and in fact, if you take it to be over 1, is the compact subgroup given by the units, and the Riemann units, not norm 1, just the units in the various completions of O. Well, they can show there's a unique model of X01 such that, well, X, first of all, X, if you extend X to C, then it's one of the connected components of this general curve. This curve in general has more multiple connected components. Moreover, the field definition of X is exactly the thing that corresponds to underclass theory, to the field which you get when you replace this by plus or minus 1. But this is the narrow Hilbert class field. So you know where to look for the model, canonical model X. It's a curve over the narrow Hilbert class field. And Shimura did in the following. Shimura said, this canonical model is uniquely defined by the property that the CM points, which I will not get into what exactly those are, but you can, that's to do with embeddings of quadratic fields into this B, that the CM points over here, they define appropriate ray class field extension of H. So if you want all these coordinates to be super nice arithmetically, then there is such a model. And it's a miracle that this exists at all. Not that it's unique, but it exists is a miracle. Okay. Now, how do you get to X? You do it like this. You know the bed primes of X, and those are the primes dividing X, the discriminant of B, the discriminant of the quaternion algebra, so all the primes where it's not a matrix algebra. You also know what the trace of Frobenius of X and its good primes are, because it's a generalized Eiger-Shimura formula. And finally, you know what the evaluations of the J invariant of X and the bad primes are. That is some dual graph theory. And for example, this second thing over here, that is very useful if you know X up to isomorphism over C, which you know if you're in the Bailey case. Huh? If you're in this one of these 14 to 27 cases, you know X over C because you have found this map, but you don't quite know it over this canonical field H. And how do you find the right twist that you need in general of such a curve? Well, the traces have to match up. And there's only one twist that will do it. And that has the right bed primes. So that's how you just cheat your way out. And you can do even more disgusting things if you don't have Bailey maps. So that's what I did in my thesis. You just use these valuations, and if you then search through the moduli spaces, you can actually find these curves, and you use modularity techniques to show that certain guesses that you make while running through these moduli spaces, they are actually the curves that you need. So I wanted to stop there. I just want to mention that, yeah, so the Bailey case is one in which all these maps, they're much more constructive. And in which case you can find the accessory parameter. The case in which you do not, you can still find X essentially by a huge box of tricks. However, things like computing the accessory parameter, in those cases, to my knowledge, they are still open. I tried to do something in that direction, it didn't quite work out, but who knows? So yeah, there's a bit of a dichotomy there, and that is what I want to stop on. So thank you very much for your attention.
Okay, thank you, Jeroen, for I will give up. Okay, any question? Recorded one? Maybe first of all, nobody asked question. Okay, I will do my own question.
Great.
This model for your elliptic curve, you do it for all 75 or 74 class, or
yeah.
And at the end, for me, this X and Y are they must be modular form over for this arithmetic Fuchsian group. Do you construct X and Y explicitly?
No. So yeah, that's a good one. In the Bailey cases, yes, because that's how the whole thing comes out, because you can just express X and Y in terms of certain Q expansions. But in the non-Bailey cases, no. In non-Bailey cases, just said this is some equation, and I know that this is true because of modularity techniques, but that's to me a completely mysterious black box.
Okay, then you use the website LMFDB.
No. There was some. It didn't come from there. It was another search. They are not an LMFDB because, for example, well, I'm not sure, but let me see. Okay, there are elliptic curves of a number of fields in here, but okay, well, by now they may be in there.
I see.
But at the time, this didn't exist, and the fields also get a bit complicated occasionally. So, no, what I did instead, I ran through a moduli space of elliptic curves, and from this knowledge of these evaluations of J, I could thin that down sufficiently so that in the end I found the right J invariance.
Okay.
Yeah. So.
Okay, maybe I stop recording, and maybe the people will get more courage to ask questions.
Okay.